Okay, good morning, everybody. So my name is Nathalie Job. I'm professor at the Department of Chemical Engineering at the University of Liège in Belgium. I was a reviewer for this thesis, but I will also have the pleasure to act as president today. So I will first introduce the jury of this thesis. So we have the pleasure to listen to EFFRAIMOPOULOU today. And the jury is composed by Aurélia Charlot from INSA Lyon, Sylvie Callas, maître de conférence à l'Université de Montpellier online, Merima Hassani from Chalmers University of Technology in Sweden. Then we have Wim Malfay from EMPA in Switzerland, Zurich. Then Gino Mangente from Cargill. And then the people who directed the thesis. So we have Julien Jaxel. We have also Arnaud Regacci and Tatiana Buttova. So Mrs. EFFRAIMOPOULOU, you will have 40-45 minutes to present the work to the audience. And then there will be a question from the jury, obviously. And yeah, we're listening to you.
Thank you very much. Okay, so thank you everybody being here today. Good morning, everyone. I will present you today my work on pectin-based aerogels for thermal superinsulation. This work is a joint project between PERSE and CMF institutes from École des Mines de Paris, and it's in the frame of the Transition Institute 1.5. So I will start by introducing you in the topic of my work. Then I will share with you the main results that we obtained, and we'll close with the conclusions and prospects of this work. Starting with the introduction, we know that we face a big problem nowadays with energy consumption, and we have a huge energy consumption coming from the building sector that is consumed for heating and cooling, and this is mainly to insufficient thermal insulation. The most common insulation materials used have thermal conductivity in the range of 0.03 to 0.04 watt per meter Kelvin. And the lower is the thermal conductivity of the material, the better is the insulation efficiency that they have. At 0.025, we have the thermal conductivity of air, and all materials that possess lower thermal conductivity are considered to be super insulating. In this area, the only solid materials that we can find are aerogels. What are aerogels? Aerogels are open pore nanostructural materials that have high surface area, they have very low bulk density, and they have a very high content of porosity. They can have different chemistry, structure, and shapes. And right now we can find commercially available, not in the neighborhood store, let's say, but we can find silica aerogel blankets that have the lowest thermal conductivity. The lowest thermal conductivity that is available for commercial products at 13 milliwatt per meter Kelvin. However, they are very expensive and they have poor mechanical properties. And for this reason, more lately, synthetic polymer aerogels were fabricated to overcome these problems. However, they have a bit lower performance, so higher thermal conductivity. What we want to do is to pass to biopolymer aerogels, so to have natural products that are non-toxic, biodegradable, and come from waste valorization. Let's see how biopolymer aerogels which are biopolymer aerogels. Usually they're from polysaccharides, protein, or other polymers coming from biomass. And from this family of materials, we know that pectin aerogels possess one of the best properties regarding thermal insulation. We can see here that for a range of formulation, we have super insulating properties, and we can reach down to 15 milliwatt per meter Kelvin, so much below air. Pectin is usually extracted from citrus peel and apple pomace that comes from waste from the industry. It's a natural heteropolysaccharide. It's water soluble. It's used in the food industry as for its gelling properties, and these properties depend on the degree of esterification of pectin, on the pH of the solution, and other parameters. Pectin, because of its structure, is very highly hydrophilic, and when we want to use it for materials engineering, we notice that there is a very rapid aging, a problem that we see with a lot of biopolymer aerogels, and we have loss of the insulation performance that we can see in the graph above. So the first question that we have in my thesis is how to make pectin hydrophobic. Next, a very important parameter for aerogel materials is the drying technique that we use to obtain the structure. We start from a solution in general for aerogels, creating a gel and then drying to obtain the final aerogel. We can use evaporative drying. In this case, we have huge capillary stresses on the walls, and then we obtain very dense structures like this. We can use freeze drying, where we freeze the solvent and sublimate from the pores of our gel. And in that case, because usually water is used as solvent, the ice crystals that grow lead to these big pores inside our material. Lastly, we have supercritical drying, and we refer to these materials as aerogels in this thesis. And in this case, we eliminate the capillary stresses in our structure, and we can obtain a very fine nanostructure network. And we can see here in this picture that we have very small pores and a very nice structure with fine walls. There is work done to bypass supercritical drying and obtain materials with good properties by evaporative drying, and only for silica and cellulose these have been achieved so far in the literature. So the next question is how to make aerogel-like pectin materials without the use of supercritical or evaporative drying, or freeze drying, sorry. So with evaporative drying. The goal of my thesis is to have a super insulating material, and starting from pectin aerogels that we know that have very good properties in terms of insulation. We want to use it for energy applications, mainly focused on buildings and construction as thermal insulation, but a lot more applications. Our goal is to have a material that is bio-based, non-toxic, is durable, is thermal super insulating. It comes from green chemistry roots, and it's cost efficient, so it can be implemented in the everyday life. For this reason, as I mentioned before, we need to work on the properties optimization of our materials. So we need to hydrophobize pectin to prevent aging. And next, we need to work on the process optimization in order to avoid supercritical drying and reduce the cost of our final material. When I started my thesis, we had a very big gap in the literature considering this topic. So in general, for pectin hydrophobization, there are practically no works. There are some modifications, still not allowed, but nowhere is mentioned hydrophobicity of aerogels or pectin itself. Then there are no data about aging of bioaerogels. In few publications, some people mention 1 day of aging, and it was never successful to keep the properties. And then for avoiding supercritical drying, we only know for bio-based aerogels for cellulose one work with specific fabrication process. So we needed to start from this. And what can we do to meet our goals? Here is the general scheme of pectin aerogel fabrication. So we start from a pectin aqueous solution. We create a gel by non-solvent induced phase separation, and then we dry with the supercritical carbon dioxide to obtain our aerogel material. We had different approaches, so we could work in all different steps of the synthesis. We tried to work with the dry aerogel, and in this case, we performed chemical vapor deposition of silica phase. Then we've worked on the organocell phase so that we can keep the structure after coagulation and obtain the superinsulating properties. And we did modification with isocyanates and modification with amines. And we've worked also on the pectin solution in order to optimize the process to avoid supercritical drying, and this by doing the coagulation in alkaline media. Let's start seeing some of the results. So starting with the pectin silica composite aerogels, we did chemical vapor deposition of methyl trimethoxylane on our final aerogel. So we worked on the dry material, and for this work we used high methoxypectane. We can see here the aerogels were placed in a closed container with a reactant and the catalyst, and they were left so that the silica phase can be developed. And we varied parameters, we varied different parameters as the initial concentration and pH of pectin solution, the non-solvent used for coagulation, and the duration of chemical vapor deposition. Now, I will give you an example for one formulation starting from high methoxypectane solution of 28% at pH 2. This is the properties of the neat material. So we see low density, high specific area, and low thermal conductivity. And after 24 hours of chemical vapor deposition, we see that we have a huge increase in bulk density and a decrease in surface area. However, we get hydrophobic materials, which was our goal. We saw, when we see the structure with scanning electron microscopy, that inside our network, we had the formation of some silica nanoparticles, which appear to be non-dense, as we saw also for the surface area values. So we wanted to adjust our process to avoid the formation of these baits. We tested to see if the silicon was distributed in the network. So from interior pieces of the material, we could see that silicon was very homogeneously distributed. So the reaction could reach all the parts of our material. We continued further by adjusting the duration of chemical vapor deposition, and again for the same formulation, for this formulation. 2 hours, 5 hours, and 16 hours. Okay. And for this case, the bulk density is increased when we have high deposition time. The surface area is decreased. Thermal conductivity increases as well. The contact angles, we can say that they stay almost stable regardless the time. But when we see the contact angles in time, not the contact, we see that when we have 2 hours of deposition, the contact angle is decreasing a lot and the droplet is eventually adsorbed from the material. In order to evaluate if our materials are stable in moisture, we do aging studies in 25 degrees and 80% relative humidity. We see first the neat pectin aerogels. So we can see, as we expected, that in the first day in these conditions, we have a huge decrease. We have the most increase. We have moisture uptake around 15%. Then we have a huge increase in bulk density. So we have 8 times the value. And this happens the first day, and then it continues to increase. And the same happens for thermal conductivity. So as we said, the unmodified pectin aerosols cannot be used as insulators as they are. When we do the deposition of the silica phase, we can see that the moisture uptake decreases a lot. So it's almost half. Then the bulk density increases slightly in the first day, but stays rather low compared to the neat pectin aerosols. And the thermal conductivity increases more substantially. This is the red line when we have 2 hours chemical vapor deposition, and for 16 hours deposition, the thermal conductivity stays nearly stable for the whole duration of the test, that was around 250 days. So in general, we saw that for the composite materials, we have better stability, and we have lower moisture uptake and density increase when we have a longer deposition time. And for 16 hours chemical vapor deposition, we have stable thermal conductivity. However, we're not in the superinsulating area. Coming back to our objectives, for the properties optimization, we wanted to obtain hydrophobic, non-aging, and superinsulating materials. And for the pectine silica composites, we were able to achieve the first two goals, but not to get the superinsulating properties. Now, the next approach that we had is to modify aerogels to graft the aerogels, and this was by modification with amines. In the general scheme, now we've worked with the organogel, so we are in heterogeneous reaction, and we used low methoxypectine at 3 weight % and pH 2 from the initial aqueous solution. Here we can see the reaction that is performed. So first step reaction was carbonyl dimidazole to activate the functional groups of pectine. And second step, we add an amine. We varied a lot of parameters for this reaction. So first we varied solvent duration and amount of CDI. And for the second step, we varied again the solvent, the duration. We used 5 different amines and also the amount of amine that was used. So first we optimized the conditions. We did a lot of test experiments, and we used the conditions that are mentioned there for the further studies. And we can see here the effect of the size of the side chain of amine on the degree of substitution of our materials. And also we can see the different solvents, how they affect the degree of substitution. So in general, we had lower degree of substitution when we were using bigger amines, and we have the highest substitution for acetonitrile. Looking at the hydrophobicity of our finer aerogels, we see that even though we had lower substitution with big amines, we had higher hydrophobicity, which makes sense because we have more lipophilic chains in our material. Some examples of materials that were super insulating and with increased contact angle, modification of the aerogels in acetone and tert-butanol. So with butylamine in both cases, here in acetone, here in tert-butanol. In both cases, we have low density, we have high specific surface area, very close to our neat materials. Contact angles are increased a lot. Here we're almost hydrophobic. And the thermal conductivity is remained very low, so as low as we have for neat pectine aerogels. However, we had a lot of challenges with this work, which is good and bad. So first we noticed that the substitution was not homogeneous. This we saw with FTIR. So we had a higher substitution on the surface of our aerogel and lower as we were going inside the material. Then we saw that we had some structural changes at the end. So we expected to obtain at the end the structure since we had performed already the coagulation of our material, but we saw that during the reaction our gel was changing, and this was not good always for density and thermal conductivity. And lastly, we saw that we lost a lot of mass during the modification. So when chains started to substitute a lot on the exterior of our material, they started to dissolve in the solvent. And for these dissolved chains, we could estimate a very high degree of substitution. So for these materials, in general, we could achieve enhanced hydrophobicity. We could reach very high contact angles, even with not as high degree of substitution. We could preserve the thermal conductivity of the structure if we had preservation of the network during the reaction. Then we could achieve a very high degree of substitution, but only for the dissolved chains. And it opens a very big door to produce derivatives of pectine with controlled degree of substitution. Coming back to our objectives for this family of materials, we could achieve the hydrophobic character. We could obtain the superinsulating properties, not in all cases, but it is feasible. And we don't have the aging data yet because of time constraints. Next, last strategy to prevent aging was to prepare pectin polyurea composite aerogels. In that case, we did modification with isocyanates, and we worked with organogel again as a heterogeneous modification. For this work, we used the low methoxypectin at pH 2. And here we see that we used the 3 different triisocyanate molecules that can be grafted on the pectin fibrils and then polymerized to create a polyurea network. We had these 3 parameters, so I will be referring to them as polyurea 1, polyurea 2, and polyurea 3. And we varied for this project the concentration of pectin in the starting solution and the concentration of isocyanate to get different content of isocyanate inside our material. Let's see first the influence of polyurea nature on our materials. We can see that the bulk density was low for all materials, but it was higher for the first and second type of polyurea used. Then the specific surface area decreased from the neat materials to the first and second type of polyurea. However, it stayed always in higher values for the third type of polyurea. The thermal conductivity was not really affected, so we see that the values are very close to the ones of the neat pectin aerogels, and we are satisfied with this. And lastly, to evaluate the hydrophobicity, we measured the water contact angle, and we can see that for the first 2 composite materials, we have increased the hydrophobicity of our structure, but we're still not very hydrophobic, so we're below 90 degrees. However, with the third type, we are hydrophobic. Looking at the structure of our material, we cannot really see a difference. So the first picture is the neat material, and then there are the other composites with similar concentrations. And we cannot see a secondary network or any particulate form. So we suppose that we have a nice coating around our pectin fibrils. Overall, we concluded that the third type of polyurea worked the best, so we decided to go with it. And also, we tested the aging and we saw that it had better stability in moisture. So going with the third type of polyurea aerogels, we wanted to see what is the influence of polyurea and see how much we can reduce the synthetic polymer inside the material. And we worked with polyurea content from 20 to 45% in the dry material. We saw that the variation of polyurea content didn't really affect the bulk density, surface area, thermal conductivity, but we had an effect of contact angle. So the materials were hydrophobic only when polyurea was more than 30% inside the material. We did aging studies in the same conditions as before for at 25 degrees and 80% relative humidity. When polyurea content was increasing, then moisture uptake was decreasing and bulk density increase was lower. For the thermal conductivity, we can see that when we have 35% polyurea in our material, then we have still, after 120 days, superinsulating properties, but only for 45% of polyurea, complete stability was reached. So for these materials, the thermal conductivity was 0.015 watt per meter Kelvin, and we have extended study than this, and we see that it's stable for after 300 days almost. And since they were the most promising materials, we tested also mechanical, acoustic, and fire properties. Very first results that I don't have time to discuss with you in the presentation, but they seemed very interesting and promising. Coming back to our objectives again, last point for the process optimization was the pectin polyurea composites. And in this case, we were able to tick all of our first objectives, to have a hydrophobic network that is not aging and super insulating materials. So now we'll go to work on the process optimization. And in order to avoid supercritical drying, we try to do pectin coagulation in alkaline environments. So now that scheme changes a bit, there is a new leg here, adding evaporative drying in order to receive zero gel materials. So when I say zero gels, I always refer to materials dried by evaporation and aerogels by supercritical drying. We worked on the pectin solution and we added base, and we used both high and low methoxypectin. We worked with different concentrations of pectin, 2 different bases for different concentrations of base, and we saw how the drying method is affecting the material properties. So first, we see the properties of the aerogels. Some examples are here. So in red on top, there is low methoxypectin, LMP, and blue high methoxypectin, HMP. And we see that there is not a real trend. The densities are relatively close to each other. They're in low levels. Then for the specific surface area of our materials, we see that when we add a small amount of base, so we are in close to neutral pH values, then we have a very high specific surface area, and the properties of our materials are very close to the ones obtained in acidic conditions. Then when we start to add more base, we go to alkaline pHs, and we see a huge drop in specific surface area. And after a point, we don't really see a big difference inside the experimental error. We can see these properties depicted on the images of our structure from scanning electron microscopy. So here we are in the low concentration of base, so in the very beginning. We see we have small pores and a very fine structure, and here we see the structure at acidic conditions. So if you put it one on top of the other, you'll see that they are very, very close. But then when we go to higher pH, more base in our system, we see that the structure changes. We have thicker fibrils in our network, and the pores start to be bigger. So for the aerogel materials drying with supercritical drying, when we increased the concentration of base, we didn't have a real effect on bulk density, but then we had a huge decrease of specific surface area, as we can see also from the structure. Coming to the properties of the zero gels, so dried by evaporation, we see a huge effect on the bulk density, depending on the concentration of base. So again, high and low methoxypectin. When the concentration of base is very low, we have very, very high bulk density that is close to the density of pectin. And as we increase the base in our system, we reach values that are very low. Then the specific surface area starts again with lower values, and as we increase the base concentration, they reach values up to 270, 80%. Not percent, sorry, 270, 280. We can see the structure again. So in this case, when we have very, very high bulk density, we can see the structure of our material that is very dense. We cannot really see the porosity. And when we go to high base concentration, we get a very nice structure. Not as nice as acidic pH maybe, but we have very open pores and well-defined fibrils. And and you can see the dust lines here are the properties of the aerogel materials. So when we're in high base concentration, the dust lines that are the properties of the aerogel materials are almost overlapping. So when we're in high base concentration, the properties that we get by evaporation and by supercritical drying are very, very similar. So for the zero gel materials, when we increase the concentration of sodium hydroxide, we have a decrease of bulk density. We have an increase in specific surface area, and we tested the thermal conductivity of the materials that showed the best surface area and bulk density values, and we saw that it was between 0.03 to 0.035 watt per meter Kelvin, which is not super insulating, but it's very low still. It's very, it's in the level of the insulation materials that are used right now. Most importantly, the most important fact was that when we had a high concentration of base, we could obtain the same materials by evaporation as we could by supercritical drying. So coming back to our objectives for the last time, working on the process optimization in order to avoid supercritical drying, we made aerogel-like pectine by coagulation in alkaline media. And we could achieve avoidance of supercritical drying. However, still we not have super insulating materials. Coming to the conclusions of my work, we started with pectine aerogels that we were very fascinating that they could be used inside the buildings as they come from the food. And we saw that not they only have super insulating properties, but they can transform in eco-friendly materials that are super insulating, that can be stable in moisture. And for us, this is a very big step to advance this kind of materials. We had to work with two disadvantages, so the moisture sensitivity and the supercritical drying. We used different approaches, obtaining modified materials, composites, in different steps of the synthesis, and we could separately tackle its problem. Then for the future work, we could say that there is room for a lot of studies. We did the first step to open the door to different families of materials. So for each different family, there are prospects to optimize the properties that we have. Then a general prospect would be to combine super insulation and durability with the avoidance of supercritical drying, so to have all in ones. And of course, other studies to see how they can implement it after environmental impact, economic assessment, and others. This work was communicated so far through one journal article and one working paper. Some articles are under preparation after the presentation. Then in several conferences as poster and oral presentations. And most importantly for me was the international mobility. So I had the opportunity to do 3 mobilities, 2 in Vienna, in Boku University, and 1 in the University of Athens, with some results you saw in the presentation. And last but not least, I would like to thank everyone. I'm very grateful for all the collaborators we had from all different departments for different properties, ideas, discussions. I cannot name one by one the names. The funding agencies, the Transition Institute. We thank Cargill a lot for providing materials, discussions, and for analyzing some of our samples. And thank you very much for your attention.
Okay, thank you very much. Oh, yeah, we'll wait 2 minutes so that those who don't stay for the question session are leaving. Oh,
I will just remove my, if you don't mind.
Okay, so we may start, and of course we will start the questions with the reviewers of your thesis. So starting with Aurélia Charlot.
There is another one next to you. Yes, yes, you need the microphone. Otherwise, the Zoom cannot hear you. Sorry. Here it is.
Thank you, Ellie. Thank you, Mrs. President. So I have 25 minutes.
Oh.
So I want to choose the more relevant questions. So to start, I would like to thank Julien, Tania, and Arnaud to invite me to review your thesis. It is a great pleasure for me to be here today. And now with you, Eleni. So I want to congratulate you for your oral presentation. It was very clear, didactic, and you chose the most relevant result among the very young experimental data that you obtained, and it was very clear. So congratulations for that, really.
Thank you very much.
Also, I want to congratulate for all your work, for your manuscript. Your manuscript is very dense, very big, but it was a very pleasant to read it, and I appreciated to read it really, because it is very well presented with a very good relevant way that you follow all along your experimental data that you presented.
Thank you very much.
And really, I was very impressed by the young experimental work that you did during your thesis, with different approaches, different routes that you developed to obtain new bioagents. And I am convinced that you bring advanced knowledge in the field of aerogels, and it was very useful for the future in this field. So congratulations for that.
Thank you very much.
And
thank you.
just the last point. So as you mentioned during your presentation, you developed a very rich collaboration in France, but not only, with a researcher from Austria and Greece. And congratulations for that also, because it is very good for a researcher. So this proves very good collaborative capacity. Okay, so now I want to follow with discussion. In fact, so about the chapter 1, and from a general point of view, so you choose to work with pectins. Okay, among the different polysaccharides that can be used for bioaerogels, and it is a question. So, okay, you explain in your chapter 1 that pectin is the most relevant candidate among polysaccharides to obtain superinsulating properties. So I wonder why pectins is the most relevant candidate. So is it dependent on the structural composition? Is it dependent on the methylation degree? It is dependent on the conformation of a peculiar conformation in water. Yeah, it is a real question. Why this polysaccharide is the best?
Yes, thank you for your question. Truth is that we don't know exactly why pectin is working the best. We know that it has this nice structure after coagulation and after cross-linking, which we don't see usually with cellulose, nanocellulose. We don't get the same structure. We get usually bigger pores, thicker pore walls, and it's not evident to achieve that low thermal conductivity. The degree of esterification doesn't really affect this property, so we tried Okay, there are some experiments that are not included in the manuscript, but I've studied the degree of esterification effect for different concentrations and pH values, and there has been done work before, and we can achieve low thermal conductivity for all materials in this range of pH and concentration. So the degree of esterification is not really a problem. Now, I cannot say, I think. I don't know. We don't know. From the literature, for example, arginate aerogels that have similar structure, they are poorly electrolytes, they make similar structures. Yes, but for cellulose, I don't know, for starts, maybe.
And compared to alginate, it is really different with pectin about the thermal conductivity?
To my knowledge, there are no studies for alginate aerogels. To my opinion, they may be very close.
Very close. So maybe the chemical structure play a role with carboxylate moieties.
The interaction, like in both cases, we start from aqueous solution. So we have the structure. When we do coagulation in the solvent, or when we do cross-linking, we don't keep the structure in the solution, but it takes it with it, let's say. So that we can start from aqueous solution and then continue, I think it's important. Also for cellulose, when it's tempo oxidized and it's soluble, it also gives better thermal conductivity. So I don't know exactly why, and I'm not sure there is a clear answer in the literature about this, but we see this trend.
Okay. Okay, and about the choice of your pectins. So I wonder what is the degree of purities of the pectin that you used, and also you choose not so much high molecular weight for polysaccharide for both LMP and HMP, and I wonder why is it choice, because the molar mass plays a role on the final cohesion of your materials. So why did you choose this molecular weight? Or do you think that this molecular weight are well suited for the final performances?
Okay, so for pectin, I know that the most important parameter on the properties is the degree of esterification. So the molecular weight may not play that vital role in our materials. I don't know if they provide other molecular weights. But we haven't, no, we haven't seen this. We have characterized our materials to see what's the molecular weight, but we didn't think to add an extra parameter to study molecular weight deviation.
And about the purities?
The purities, we have analyzed the carbohydrate polymer and ion content. Ion content.
And proteins, no?
No.
No proteins?
No, we have not. Usually for pectin, they do analysis of the sugars and the carbohydrate polymers and degree of esterification. We didn't think of analyzing. We did this externally, so I don't know where we could do.
Okay. About the chapter 3, so concerning the preparation of the composite, so you chose chemical vapor deposition. So I wonder why did you choose this silent, so trifunctional silent, and you perform deposition in vapor phase, okay, at ambient temperature,
yes,
and atmospheric pressure,
yes,
okay. And this silane at the evaporation temperature high, it seems 100 degree.
120.
So I wonder why is the choice of this silane, because it is not so volatile. Why a trifunctional silane? Because you showed that we have the formation of silica particles. So maybe by choosing a monofunctional silence, we can favor a covalent grafting and not a cross-linking. So just if you can comment this aspect.
Yes. So first for the temperature, even though it's not, it's below the boiling point, like we still have the surface with the surface tension in the closed container, we get the saturation of the vapors. So it can still proceed. There is this process also in the literature. It's feasible with the catalyst. Then why to choose this? We try to functionalize pectin with HDMS and graft, but it does not graft. And this was not even vapor solid reaction. So I've discussed with other people, it's not I don't know if we can graft it, but also it may not be very stable as bond. And in that case, we wanted the network so that it creates the network during the deposition, not just grafting, in order to be all around the fibril.
Do you think that with no grafting, no covalent grafting?
We don't know, because we wanted to see if it's covalently grafted or not, and then forming the network. And I had discussed with our NMR expert from Vienna. And we said that it will be very hard to distinguish if even with silicon NMR. So we didn't continue measuring the data. So we don't know if it's covalently cross-linked, because it could, like chemically speaking, it could graft covalently, but we don't know if it does, or it just is the polymer that forms
around the fibers.
Yes.
Yeah, with a layer. Okay. So in fact, you show that it is not necessary to have an high grafting, because if you highly if you have an high content of silan layer, you have aggregation around the pectin fibrils. So in your opinion, how it will be possible, on which experimental parameters we can play in order to have a better control of the grafting? Okay, you play with the time. It is a very judicious choice, but on which parameters, experimental parameters linked to your device, is it possible to play in order to well control the grafting, in order to avoid aggregation?
So in that case, as I said, we just put everything together, not in contact, and then we have the vapors. The other thing is that here water is inside the reaction and we don't control it. So it's the moisture of the air, and this is very important.
Yes, I think.
So first thing is to control the moisture in the container. Then to control the flow of the reactants, like MTMS and the catalyst. For me, this is the most important, because we have no control. We have the surface tension, we have vapors, then okay, it's consumed, it gets more, but we don't have real control except time. So for me, first is to control the moisture content. Maybe we could have even more homogeneous, even for lower deposition time, to have better protection of the fibrils, and then the MTMS to give it directly as a gas.
And maybe with ethoxysilane instead of methoxysilane, because the reactivity is different.
Yes,
and I think it can be interesting to test that. And in your prospects, you mentioned this vapor deposition with other kind of reactant, such as anhydrides and epoxy. I think it is a very good choice. And do you have any idea about the structure that you can use to do that?
We can use acetic anhydride, that is simple.
Yeah.
Or we can graft like as a chemical vapor deposition, and for polymerization,
which is just a question.
yes, I don't remember. I don't remember.
Yeah, and maybe with anhydride of epoxy, it will be necessary to apply a post-thermal treatment because the reactivity is not the same, but it can be interesting to do that. And also, did you try to do impregnation of your reactant on new aerogels?
I did not try this. It is in my prospects. We did not have time to try this. And it would be nice to try, because if we hydrophobize the network, it may work as silica aerogels, and then we could potentially avoid supercritical drying. But we did not try this. Yes.
To favor the contact.
Yes, because it would be a different structure, different coating, different everything, and a lot of properties of the aerogels. All the properties of the aerogels are governed from the supercritical drying. So because we have some shrinkage during supercritical drying, we have change in density, in the pore size, we assume, and then this affects directly thermal conductivity. So if we work on the organogel, we can really affect a lot our finer material, which is not bad. I mean, it has a lot of potential. It has been done for cellulose. It gives good properties, but it was done for the other way around. So silica has the super insulating properties, the structure, and cellulose was the reinforcement network for the mechanical properties. So modifying inside the pores is visible from the literature, but we haven't tried it.
Okay. So I will continue with the chapter 4 because so concerning the grafting of amine. So for this chapter, congratulations in particular, because there are a lot of experiments, a lot with different experimental parameters, and I know it is very time consuming. So congratulations for all this work.
Thank you.
So in this chapter, so I understand that the challenge is to sufficiently modify pectins by keeping the final integrity. It is not so easy to do that, and the difficulty is to modify in heterogeneous medium. And it is the case for you comparing to classical modification in solvents. It is totally heterogeneous. And the accessibility of the function is governed by the nature of the solvent that you use. So it is not so easy to do that. I have questions about the calculation of degree of substitution, in fact. So you use the infrared and carbon NMR spectroscopy at solid state. And could you give me more explanation? So I understand that with infrared, you used COC as reference bond to calculate, to have an internal normalization. But about NMR spectroscopy, which reference did you use to calculate DS?
I have slides with,
I didn't find this data. Maybe
okay.
it is given, but
so these are the NMR spectra. We used carbon NMR. We know that is not exactly quantitative.
Yes, it is semi-quantitative.
Yes, for this reason, always we are very careful to estimate the DS and not calculate.
Yes.
And we want to continue with elemental analysis for this.
Yes.
To really see what is the degree of substitution, because pectin is not, I don't know, for liquid NMR with solvent could be used. Maybe liquid NMR we could do. I mean, for the modified chains, for sure, we can dissolve in solvents. So what I used we see here the spectra of the modified pectine. In this case, is with butylamine, and these 4 peaks, so 7, 8, 9, 10 in the spectra, they are from the 4 carbons. I need to put the pointer of the side chain of the amine that is grafted. So I have taken the integrates of these peaks, all 4, and averaged them.
Yeah.
And this is how I estimate the degree of substitution.
From comparison with which peaks?
With the C1.
Okay, C1. Okay.
With the C1 of the ring.
Okay. Okay, so
sorry, just one more. Okay, it was here. So we measured for some samples, because first I have to say that these experiments, all the test experiments were performed in Boku in Vienna. And thank you very much if you're here and listening to me. And I was there for a limited amount of time, and we didn't have time to perform NMR to all of the samples. So I had done around 170 tests, and it was impossible to make an NMR. So what we thought is that if we can see that we have a good correlation from NMR, carbon NMR and IR, the band of the amide 3, then we can use to compare the different formulations and say, okay, this solvent is better. This amount really affects. And we saw that we had a very good correlation. And that's why we continued with this, even though we know that it's not completely accurate quantitative. For comparison reason, we consider that is a good indicator.
It is a good indicator
to know. So we, in this case, we see 5 the blank sample and 4 more samples that were prepared for the first study of the CDI reaction. So different amounts and times.
And just a question about the activation with CDI. So you mentioned that it is possible to activate OH and COH groups. So from your carbon NMR spectrum, is it possible, an estimation, to calculate the degree of substitution on OH and on COH through the integration of the C6 and C11 signals? You see
could be estimated.
What I mean?
Yes.
Just to have an idea.
Yes, here and here.
Yeah.
Yes.
Because you consider C7 to C10, so I think that it should be possible to decorrelate.
Sure.
1 minute. So, oh la la. Okay, sorry. So I want to stop with this chapter. So, one more questions? Oh, 2 minutes. Oh, sorry, because I have a lot of things to. It is very interesting. So, about so 2 questions about the grafting of 3 isocyanates.
Yes.
So you clearly show that this module, the 3 reactant is the best. So, okay, is the best, but same scanning electron microscopy shows that the morphology is not so different in comparison with 1 and 2. So I wonder why, in your opinion, why this module is the best? Is it the structure, the reactivity?
So
the degree of cross-linking, maybe.
Something that I didn't mention here, it is in the manuscript, but it's important now, that for the 3rd type of polyurea, for the same concentration of isocyanate used, we had the higher content. We had I rephrase. We had higher content of polyurea for the two first composites rather than the third.
Yeah.
So for sure, it's not the amount of synthetic polymer in the material. So this we take out. Then we know for the first two composites, the structures are very similar. So if you see here, we have only one carbon atom difference.
Yeah.
So we believe that is the structure of the isocyanate. And why it gives better properties, we see that during supercritical drying, we have less volumetric shrinkage. And this is directly translated in the, in the specific surface area of the material. So we have increased surface area, and we suppose something is missing. We suppose that the small pores are not closing during supercritical drying. And this we cannot see in SEM, because in the highest magnitude we can go, we cannot see the difference in this small size of pores. So we suppose that there is a higher fraction of mesoporosity that is preserved during supercritical drying. And for this reason, we have higher surface area, density is almost the same. But that's why we get better properties. And then for the stability, we see that is more hydrophobic, and this must be due to the structure.
Yeah. Okay. And the last questions. Yeah, general questions. So you develop different strategy, different approaches on organogels, aerogels. In your opinion, what is the more suited, the more efficient to develop high performance aerogels from ecological, sustainable point of view and economic point of view? Which route is the best for you?
I'm a parent that loves all of my child. So I cannot really say what is the best, because for all four that we started, it's the first that we did. So I believe that if we take each process and we optimize, we can choose more eco-friendly materials, more suitable processes, and eventually, maybe not, we can achieve super insulating properties, but they all seem very promising to achieve good properties, material properties. So I would not say, maybe not vapor deposition, because we want to remove supercritical drying. So it would be better to not have two modifications and do it at once to remove more solvent exchange steps and more steps in the process. But I would not be able to choose, I would say. No.
Okay, thank you. Again, congratulations and good luck for your future.
Thank you very much.
Okay, so I will change caps now and take my cap of reviewer for a few questions as well. First, congratulations for both your presentation and manuscript, so same comments as my colleague. I was quite impressed on how you could really direct the discussion to the points, while you start from a huge amount of data and many parameters that you really had to refine to choose where to continue. So really that was nice to see in the thesis, because you could be lost very easily in those results and all the choices that you have to do. So congrats for that. Yeah, I also would like to congratulate you for again, for the choice of the methodology that you did, especially given the fact that you started from very few information on those materials. So that's really a challenge when you start with that. Sometimes you have too many. Here, that was a bit scarce. So congrats for that as well. So that's really a precursor study, which will probably be very interesting for the next students or researchers who will come. So thank you for that.
Thank you very much.
So I'm going back to questions. So I'm not at all a specialist of pectin myself. And I just had a question about, so here you are working at the lab, so with probably high purity materials, but you state from the start that, okay, that's a waste. Okay, so it comes from apple peel or citrus peel. So what does it take to get those precursors in a refined form that you can use to do your aerogels? So my point is, if you take materials from waste or from natural resources, so we have the same problem with tannins for carbons, for instance. So how do you control the composition and what's the cost of it? So do you have any idea about the constraints that are behind that?
Yes. So in general, we get our pectin pure, so we buy it. We don't use waste. And we work with this. However, we could potentially work with waste, but we have not studied. I have colleagues that work directly with waste, and they can achieve nice properties of materials. We never need to reach food grade purity of our material, of course, and we don't mind if there are impurities in that sense, but we have not worked on the process before from waste to pectin, like pure pectin.
The question is just, okay, so those materials, so if you need to buy 1 kilogram or 1 ton of those things, so is it something that is economically speaking possible? So did you just think about that?
Yes. Yes, it is. So right now we have silica aerogels that are used a lot, and these are very, very expensive, I think. So I think pectin is a bit better. Yes, pectin is, I mean, we can have it at home. It's not an expensive product. And for our materials, we need a very few amount of pectin. We don't use a lot of material. So we're in 2%. 2%.
Still, if you had to do that industrially, you would need kilograms, tons of that. So that the point is just, okay, so can you do an industrial process with less refined materials that would be less costly than the ones that you have at the lab? So
I think that we do, but we have not worked on this.
Okay.
We have not worked at all on this.
Okay, a question about the transfer mode for heat. So you have shown that in your, so I think it's page 63 of your manuscript. So that there is a scheme of principle on how heat is transferred from one side to another, for instance, of your material. I seem to remember that on those materials, you also have the effect of dangling chains, which is not taken into account
what?
yet.
Sorry?
Dangling chains, so chains that are not connected to each other. And then that's actually beneficial to the fact that you don't transmit heat, because those chains don't, so they stop a little bit the heat to be transmitted. And I was a bit surprised that you didn't consider that effect in your materials. And so maybe I was wondering, maybe it's just because all chains are indeed connected to each other. So do you have any means to check that? Especially given that if you compress, well, you see also effects. So what do you think about it?
We don't know if we have free chains that we don't know the connectivity of our network. What we see is that we have a well-connected network when we observe our materials, but no, we have not seen this. We know that it will affect thermal conductivity, but we haven't tested, okay, this thermal conductivity of pectin is that low, why? The structure, the interconnectivity, the thermal conductivity of the backbone, this we have no measurements.
So that, I think that's something that should be maybe later, of course, later in the work, because that's probably a factor that could explain some differences. Problem being that when you observe those materials with SEM, for instance, you just have some kind of projection of your materials.
Yes,
you don't really see those effects. They're very hard to observe by SEM actually.
The only, so if I may, the only thing, because we could do some studies, is that we need very big materials, and this for us was a constraint as well, because we need specific dimensions, big boards to see the solid phase, conduction, and everything. So this was also, we consider it, but it was not possible to do, considering also that pectin is aging fast, it was a bit tricky.
Okay. So about so it shouldn't come as a surprise in my questions, but about characterization of the materials. So you report two descriptors mainly, so that's the density and the surface, specific surface area measured by a nitrogen absorption. So yeah, that's what I was missing in your thesis. So my question is more, okay, what do you consider to be the ideal structure of materials that you should reach to have something that works well? So in terms of pore size, indeed, and yeah, and pore size distribution and so on.
Sure.
I'd like to comment this.
So yes, thank you for this question. Truth is that this was something that was left out by mistake. So it should have been in the manuscript, but it was forgotten out. So we know for pectin aerogels that when we have the nitrogen isotherm and we use the BJH method to calculate size distribution, we get a very small fraction of the pores that is considered. So here is an example. I have measured for a lot of materials the whole isotherm, and we calculate some pore volume. And the volume that we get from 1.7 to 300 nanometer is usually below 5% of the volume fraction that we have in total. We don't know.
20 cubic centimeter per gram. So what? That's enormous. Okay. The volume of pore calculated. So I read 20.2 cubic centimeter per gram.
Yes.
So okay, and the amount that you have below 300 is only 0.7.
This cannot be true, to be honest,
That's
according to
strange.
us, because we know that we're in the super insulating area. So we know that we don't have pores above 300 nanometer. At least not 95% of our pores are above 300 nanometer. So we have observed this problem with bio-based materials. We are trying to discuss with the company to understand why.
But there's something very strange here, because 300 nanometer, that's in the macropore data, and you cannot access macropores with nitrogen absorption. I don't understand those values.
This is the values that are given from the nitrogen absorption from the BJH method. This is the report of BT. The BJH method always gives data from 1.7 to 300 nanometers.
That seems strange to me, to be honest, because here you stop your, well, at relative pressure 1, that's 50 nanometers. So that's the limit for nitrogen absorption. So I don't understand why it is mentioned 300.
50 nanometers.
50, yeah, that's the limit for nitrogen absorption. You cannot go beyond. So I'm a bit taken aback. So I would invite you really to check those values, because that's probably not so right.
I'm confident. First of all, this is the value that is given directly from the nitrogen absorption.
The total,
so it's given from the machine itself. It's not calculated by me.
Okay.
Then we can calculate the pore volume, so the upper part, from the skeletal and bulk density.
Okay. So which means that you have a lot of macropores that you don't see.
We don't suppose that we have micropores. We suppose that probably the method is not suitable for our materials.
So I don't understand then the discrepancy. I'm sorry to insist on that, but 20.2 versus 0.69. So what's the difference?
So that's what I'm trying to say, is that we know that we have a volume of pores, and when we do the measurement of nitrogen absorption, the BJH method that was supposed to give us the pore size distribution considers only, in that case, 3% of our pores. So we after discussing, we say that since this model does not consider our pore volume as whole or a big fraction of it, we cannot say that, okay, we have an average pore size at 20 nanometer, because this would correspond to a 3% of our volume.
Yeah, there's definitely something strange. I agree with you.
But
okay.
We are in discussion with the company, and even them, they don't know. So we try to understand if it's a problem with the technique or the method. We try to solve this, but this is a problem in general for bio-based aerogels. So for cellulose, pectin, I guess for all bio-aerogels.
Because if you just look at the volume, you can just take the value at relative pressure equals 1 and convert your adsorbed nitrogen in STP into a volume of pores. So that's just quite direct. And so probably it corresponds to 0.7, but then I don't know where the last 19 cubic centimeter are gone. So yeah, okay.
So for this reason, after we say that we cannot consider the method for the pore size distribution, we measure surface area, but we cannot consider it valid for pore size distribution. We choose to not expose it as a measure for pore size distribution.
And did you consider mercury porosimetry? So does it crush the material, or is it...
We have not tried. So not mercury porosimetry, conventional one should not work, because
you crush the material? Yeah.
We have very low pore size, but I know that
it's still possible to make some evaluation. So if you know these struts, yeah, that's feasible even for crushing, but not with Washburn's law. So that's but maybe it could be considered as alternative.
Yes. Also, we could consider also thermoporosimetry, but we don't have any of this equipment, so we could not evaluate.
Okay. Another technical question. So very nice to have those curves for aging in a humid environment. I was wondering again. So again, that's probably a question of equipment. But do you think that DVS, so dynamic vapor sorption, could bring more information to your system? And what type of information could you get from that? Apart from just, okay, we take water and we store water inside the material. So would it be interesting?
Yes, sure. It will be interesting, especially at the very beginning, that we have a huge increase of moisture to understand, to have always a closed system to see what is happening. And we're trying to obtain the machine, but we don't have it. So we do measurements of the weight. Yes, hopefully more funding is coming.
Yeah, so about drying now, so we've compared different techniques, and I'm happy to see things going to evaporation, because that's indeed something that is always taking aerogels back. So that's the CO2 supercritical drying. But my question is more about freeze drying. So you've used freeze drying, and especially turbotunnel to make the technique work. Two questions here. So I've seen that for freezing, you are freezing your materials in a freezer at minus 80 degrees. It's not always the fastest, because contact with gas transfer with heat is not very fast. So have you tried to freeze your materials in a liquid bath at minus 30 degrees of alcohol? That's fastest.
Yes, so the freeze drying was used only for the grafting of amines, and only to dry the materials without passing from high temperature technique, so from oven, in order to do characterization. In these materials, we did no characterization of material properties in terms of density, contact angles. So what we did, again, it was not possible. Also, supercritical drying is not always accessible in the lab, in different labs. So, okay, here we do supercritical drying, but when I was visiting the other department, it was not easy to do supercritical drying every day. And so in order to evaluate the degree of substitution, in order to dry our materials, we were doing freeze drying in order to not have an effect from temperature. And we didn't care about the properties. We did all the tests to make the optimal conditions with freeze drying. And when we optimized the degree of substitution, we applied the same chemistry in the gels and we dried supercritically.
Okay, so I get the idea there. Just a remark. So in the third butanol, that's something that doesn't expand upon the freezing, but still you grow crystals inside the material, so you change totally the texture of the material, whatever you try to do, because crystals. The only option is to speed up the freezing so that crystals don't grow too fast.
Yes.
So it remains small. Okay. So I'm just going through my questions. A question about the last chapter. So regarding the use of bases. So finally, you conclude that it's better with sodium than potassium, if I remember well, and that's because of the size of the ions. So maybe the charge also has an importance. So I guess you should consider, and you have that in mind.
Sure.
Double charge ions.
Yes, sure.
And what about smaller ions like lithium?
Okay, so we don't know exactly what will happen. We need to do a really good study to study the metal ion and if the hydroxyl ions really have an impact on the structure and what really is there. So we have theories like the metal size, the ion size, and the radius and I'm losing my English. I cannot find the word. Okay, anyways.
Both the radius and the charge have an importance, I guess.
Yes, both, and they're not exactly. So sodium should be more smaller, but more hydrated, high radius, hydrated, and same charge, like the ionic charge is the same, but it has stronger charge, sodium. So this already we see a difference in the structure. So we wanted to study in terms of the Homeister series to see if there is an effect there, then to try non bases without hydroxyl ions to see how it will affect the structure. And there was another question. Sorry.
So that was also, well, if you use smaller ions like lithium, for instance, would it change things in your opinion?
Yes, probably. Because for sodium and potassium, all the works that exist in the literature with pectine and similar materials, they see practically no difference. They have never reported something. For depolymerization, esterification, everything, they say, okay, these are the same. And we saw that they're not the same at all. So for sure, if we change the metal ion, it will change. We expect to change, but we don't know how.
Thing is that I'm not totally sure to understand the mechanism of formation of the gel. So we often see in literature that you can destabilize colloidal suspension somewhat by adding some ions. So and indeed, hence the Hofmeister series. But here, if you see actually a difference with NaOH and KOH with the same pH, so probably there's also an effect, as you said, that with the contact between the ion and water also might be, or the solvent might be also.
It is interesting because when we add high amount of either sodium hydroxide, either potassium hydroxide, we have a coagulation. We don't know exactly what is happening, but we suppose that it's a coagulation due to the ionic strength of our solution. And this, both for sodium and potassium, we have coagulation for the same amount of base. But then the structure of the network is very different. So first we have a coagulation of the structure because of the anionic strength. And at the second step, we have a different mechanism of chain association that's very much dependent on the metal ion. This is what we suppose. So we need to see we see that the ionic strength is the same, they have the same effect, but then we need to understand the metal ion exactly what is the mechanism.
Do you make any distinction between coagulation and phase separation, actually? I'm not familiar with the terminology, actually.
I usually refer to them in the same way.
Okay, so that's the same thing. Yeah, so meaning that screening of charges and stuff like that will also apply to that system. But yeah, that's a big soup, so that's very difficult to control. Okay. Yeah, and maybe one last question, because I'm running out of time myself, so I have to discipline myself either. So about mechanical properties, so you mentioned that one of the biggest problem of silica aerogels, that's indeed their mechanical properties. So how do you compare to those materials with those properties?
Okay, so for nitpictane, there are some works in the literature, but we have not measured exactly ourselves because of the aging. But we measured only for the polyurea composites. And okay, we are actually good because we have a good compressive modulus compared to silica, and we don't have rupture of our material, so it can be compressed. This for the composites. We haven't done mechanical properties. We haven't measured mechanical properties for any other things. And for the level of thermal conductivity that we are compared to other materials, we are also very good. It's the last graph on the right. So I think they pass as materials because for insulation, materials can be used in very different forms and they can have very different properties depending on how you do the installation. So we don't have any release of dust or rupture of the material. I think it can be cut. I mean, I haven't tried to manipulate it and cut it with
It doesn't erode or becomes
nothing.
dusty or whatever.
No, nothing. Okay, it's a nice board that stays there. If it doesn't age, it stays there. And everything is good. So the mechanics for insulation are good.
Okay, thank you very much. So I will stop here and congratulations again.
Thank you very
this
much.
Very nice work. So the next person who will ask question is Sylvie Callas from Montpellier. So she's in line, please.
Okay, yes. Could you hear me? Is it okay for you?
Yes, yes.
Okay. Okay. First of all, I would like to thank Arno and Tanya to give me the opportunity to follow this work. Unfortunately, I can't be with you in person today, and I'm really sorry about that. Eleni, your research fits into a very sensitive context, thermal insulation materials that are not only highly efficient, but also able to meet today's environmental and energy challenges. And we know that aerogels are good candidates for this. But there are still barriers to overcome, and you are doing here a very brilliant job to tackling them. So I would like to join my colleague in saying that your presentation was very clear, very pedagogical, and very easy to follow. Congratulations.
Thank you very much.
It's the same thing for the manuscript. Very well organized, very effective. As my colleague have already said, it shows impressive work in several levels. First, the large number of experiments you carry out, very impressive. the detail, synthesis, and characterization, very convincing analysis. And at the end, the achievement of innovative work, reference level work for me, in the field of bio-based aerogels. So for some of the points I wanted to raise have already been covered. So you have already answered many of my questions, especially on pore structure characterization. If we can go back to the discussion on that, when you make nitrogen adsorption and use BGH method, indeed the structure crush and come back when pressure decrease. So you only measure just a few parts and something very little part of the pore structure. But there is something strange. I'm agree with my colleague. There is something strange on this data. But there is an adaptation of the BGH method which could be done. But it's very difficult is to increase the time during manipulation. It's manual technique. It's very difficult. It could increase it could optimize the measurement, but it doesn't work for all materials. It's the same thing with mercury posimetry. It's very difficult because the structure crush. Some question for me on chapter 3 about pectin silica composites. You analyze by EDX analysis. Did you analyze several areas of the materials? It's for the manuscript on page 100, I think. Did you analyze several areas of the materials? And did you observe the same behavior everywhere?
In terms of homogeneity or in terms of constitution?
Homogeneity of
yes, for the homogeneity, we tested some materials, not all.
Yes.
And in all cases, we had homogeneous distribution.
And for one materials, a different part of the materials.
Yes, I think we do 2 points usually.
Okay. And for the contact angle measurement, it's well known that they depend strongly on the surface roughness, but not only on that. You mentioned that the increase of angle is only due to polishing. How can you be sure of that?
Yes. So
it's on page 101.
I remember the graph.
Yeah.
Yes. So the idea for this was to see if the hydrophobization is all the way through the material. And pectin aerogels, when you have a disc, to remove parts of the discs, it's not easy to cut it with something. We tried with different things. We didn't manage well. So we thought that the best thing is to polish to get a flat surface. And I can see for materials that I know that are homogeneous, not need pectin, that when I polish the surface, I have an increase in contact angle. So moving inside the material, I suppose that it's not that we get more hydrophobicity, like more deposition of silica or something, but this big difference in contact angle we mainly attribute it to the polishing, so the roughness of the surface after polishing.
Yeah, between neat aerogels and the other one, but are you sure that only the polishing and there is not another thing which can explain
no,
increasing
I mean,
of angle?
It could be the roughness of the surface itself on the surface of the aerogel and the interior of the aerogel, that we know that the roughness is more inside, but we cannot distinguish what it could be.
And
we tried to cut better, but we did not.
It's very
manage.
difficult. Okay. In figure, always on angle contact, I cannot see the variation of angle. Are the variation of angle very significant? I can clearly see the uncertainties. So you systematically reported measurement uncertainties, which is very great. Thank you for that. But you didn't explain much about how you measure the uncertainties. And for this, for example, are the variation of angles significant or not between all the R% difference?
Okay, so usually when so only for the contact angles, right? The variation.
Yes.
So for the contact angle measurements, usually I measure 1 or 2 materials and at least 2 or 3 droplets on the surface. And I get the variation. Usually I get very consistent results. So the variations are very small.
Very small, okay.
Yes, for the contact angles.
And for the other one, how do you evaluate the uncertainties? For example, for thermal conductivity?
So usually for all values, for all materials that are prepared, I have measurements from different batches of materials, so prepared different days.
Mm-hmm.
I have from each batch at least 2 or 3 materials, and usually I don't measure the same material 2 times.
Okay.
So I have different batches and different samples from the same batch, and this is how I extract the standard deviations for all of my measurements.
Okay, thank you. Okay, in chapter 5 about pectin polyurethane composites, just first question, why does the addition of polyurethane sometimes reduce the thermal conductivity compared to pure pectin?
Mm-hmm.
Even if the density is almost the same and even slightly higher. Do you know why the addition of polyurethane?
Yes, we have some idea for this. So as I discussed before, we think that when we add polyurea in our material, during drying, we don't have a closure of very small pores. So for this reason, we think that we have higher surface area and lower thermal conductivity.
Okay. Okay, just the surface. Okay. From mechanical properties. So on your manuscript, 187 page. You study mechanical properties under uniaxial compression. Could you show me more precisely how you proceed? How did you define the linear part of the curve? How did you exactly calculate the absorption energy? There are not many details in this section. So could you explain a little bit?
Yes. So the linear part of our curves we defined together with our mechanical properties expert, I would say, because I'm not an expert myself on mechanical properties. And the absorption energy is the area, I think, till 40%. I'm not sure. I don't remember. I need to see it. Okay, I need to add this. I'm not sure, but is the area below the stress strain curve up to 1 strain, 40%. 40%. But I will need to add the equations. Yes, sorry for this.
Okay, it's okay. You said that the Paul law doesn't apply because the composition changes. Do you remember that or no?
Yes, sure.
Okay.
So
do you mean the exponent change?
Yes, the constant.
Okay.
So we cannot correlate them because we studied different materials of different composition, and we didn't correlate them with the power law for this reason.
And for you, is it possible to link the for one composition? Is it possible to link the value of n to the structure of the materials, to the evolution of structure?
The value, the constant.
The value of the constant n in the power law?
We need to have materials in different densities for this.
Yes, and you have not. Would it be interesting for you? This is the question.
It's a bit tricky because we have a double network, and I'm not sure how we can vary the density and keep the rest constant. For example, if we have neat pectin and we change the concentration and different parameters, we can achieve different densities. But then for composites, we start to have different biopolymer, synthetic polymer ratios. I'm not sure how it can work.
Okay. Because it would be interesting to
know this, yes.
To know this and to compare, to join with the evolution of textural.
Yes, sure.
Properties of the matter. One last point: why did you test the mechanical properties of these materials and not the other one? This is not a criticism. It is not just a question.
Yes. So we tried to get the best formulation we had. So the best in terms of stability and moisture, and then explore further the properties. And for this reason, we have gone with the highest concentration of polyurea for the third type of polyurea. We tested both concentrations of initial pectin solution because both concentrations were stable. So the same we did for the other, like for acoustics and fire properties. We just took the best formulations in terms of stability. That was the most promising material, and explored further properties that are relevant to construction materials, thermal insulation materials. No other reason. We tried to do pectin to compare, but due to aging during preparation of our materials for a compression test to have parallel surfaces, they were already aging. Density was almost double before we started the test, so we could not really consider it in the study. And okay, always the biggest limitation we had was time, to be honest.
Okay, yes, and you could say to me that even it's another subject of another PhD, maybe. Okay, once again, Eleni, thank you and congratulations for
thank you very much.
Such a work, rich, complete, convincing, and which clearly demonstrated your excellent mastery of the subject. Thank you.
Thank you.
Thank you very much. So we go towards Professor Hassani for next questions.
Okay, thank you. First of all, I would like to thank your supervisors for inviting me. It's a great pleasure being here and having opportunity to discuss your fantastic thesis. And saying that, I will also like to join my colleagues in congratulating you on this fantastic work. I mean, it is a very impressive, the amount of work you have managed to do. You also mentioned the impressive amount of samples and the experiments you have done during your time in Austria. So it's also it adds to that. So really, congratulations.
Thank you very much.
You presented it also very nicely, very pedagogically, and I can also say that the written thesis was very easy to read. It was well structured, and every time I wondered why didn't they do this, then you proved me wrong in the next on the next slide. So, and every time I also needed a reminder how certain experiment was done, the reminder was there in the text. So it was very, very easy to read, and I learned a lot. So thank you for that.
Great, thank you.
I have a lot of questions, but we are on a tight schedule. So I will actually start with to me, the most intriguing part of this thesis, and that is the very last chapter, where you worked with gels from alkaline solutions. And there you could see that you could obtain gels from alkaline solutions that could withstand evaporative drying much better than the gels you prepared in the beginning of your work from acid solutions, which might mean or have to mean that we have a different mechanisms for gelation, right, from these two systems. So can you comment on that? Have you been thinking around it? How are gelation mechanisms different at, for instance, pH 2 when you add ethanol as an antisolvent, or in the case of adding sufficient amount of sodium hydroxide to induce gelation?
Sure. When we make pectin in acidic conditions, in order to obtain gel, that we say, we do coagulation in the non-solvent, so we only get the structure because of the solubility change of our pectin chain. When we use a high concentration of base, we get already a coagulated network without adding a non-solvent. So in these conditions, pectin is not soluble anymore. So as I said, we think, and from the theory and other studies, that the ionic strength of the solution is what governs the phase separation of our system. So for sure, it's a completely different mechanism.
Yeah, and what do you think are the structures in your pectin that are responsible for this phase separation? Because something drives your polymer to form a gel, something drives the chains to associate with each other in both systems. So what do you think is difference between these two? And I mean, I don't have a clear answers either. I have some theories, but I'm very curious to hear what you think.
For the acidic, for the solvent in acidic media, I would say hydrophobic, hydrophilic interactions govern more the structure formation.
Yeah. So what are if you imagine your pectin at pH 2 when you keep adding ethanol, when it starts associating, what are the structures on your polymer that drive this, or that are active in this association? I mean, you mentioned, for instance, hydrophobic pairing, right, in your thesis. So there are groups that are less hydrophilic or more hydrophobic during this process, right?
Yes, but exact interactions I've never seen in the literature, actually, to be honest. I didn't think about this.
Okay.
Yes.
I mean, when you...
I don't know if there are studies about because coagulation, like, sorry if I interrupt.
Go ahead.
This pectin in non-solvent doesn't really happen a lot. So coagulation in a non-solvent is I think it's a Sophia Antipolis thing, maybe, mainly. I'm not sure someone has studied this, the interactions.
Okay, but I mean, you agree that charge and your methyl esters are important here, right?
Yes.
The degree of charging, or the fact that you lose a charge when you decrease pH, for instance.
Sure.
That must be important driver when chains associate to each other, right? But then in alkaline solution, the situation is different. Because what is the main difference then when you are in highly alkaline solution?
Not really any difference, I would say, because okay, now I come back to the characterization that I didn't have time to mention during my presentation. Oh, okay, so we know that when we're in high alkaline conditions, from the spectral changes in the IR, we are completely deesterifying the pectin chains. And then in terms of molecular weight, we saw how it changes because we expected it to change a lot. And we saw that we're deducing a lot, but we're not very far from high and low methoxypectin. So when we at the base, at the end, after base is acting in the system and is mixed, we consider that the chains that are in there are similar. So I would not say that the degree of esterification or the molecular weight have any effect on the
No, probably not. I mean, yeah, degree of esterification, you remove your esters, so they don't matter anymore in alkaline solution, right? And what about the charge effect in alkaline solution?
The charge effect for the chains, the pectin chains.
Yeah.
So in general, from the literature, when you increase the charge, you are supposed to have repulsion of the chains and then reduction of the viscosity of the solution. And this we see, but we see it up to pH 12.5, 13. And then suddenly we have something that's going on there.
Yeah.
And so in the literature, there was one more work that they've noticed this phase separation. And their theory was that there is a silting of the ionic the ion of the carboxyl ion, and then it interacts, chains interact, and I'm not sure what this publication wanted to say, but sorry.
Yeah. Yeah, I mean, it's not easy. The system is very special, and as you say, at high,
it's a bit tricky.
It's a bit tricky, yeah. And I think that the charge does not matter anymore in this system because you have so high ionic strength that you have very strong shielding effect. And but you do discuss the salting out effect.
Yes.
Yeah. So how do you understand the salting out effect driving the gelation?
So because of the ionic strength of the system, that pectin is not soluble anymore in water in a system of that high ionic strength.
So what happens then when you keep increasing the base concentration?
So the water likes more to be with the metal ions, and it goes far from pectin, to say simple, and then pectin stays alone at the corner and just
I mean, exactly. Roughly what you described. I mean, by adding more base, you basically create solvent that cannot accommodate polymer anymore. So it is more prone to exclude polymer.
Yes.
And that's what you very clearly see with sodium hydroxide. But then with the potassium hydroxide, you don't really see that, or you see still salting out effect, but you don't see that high effect on the strength of your gel. right?
I do see, no, I do see the effect on the ionics of the ionic strength. I get the coagulation. The gels are very similar that I obtain. It's just the structure at the end that it's very different. And this, I don't know how it can correlate just with the ionic strength of the solution, because the amount of base in molarity are the same, so the pH should be the same. And
but exactly, that's what you partly discussed with Natalie before. Of course, ionic strength is an important factor, but it is also the structure the cation makes with water. So that was a bit what I was missing in your discussion, because you discussed quite a lot cation interaction with the pectin, but the interaction with water and how you change the structure of water with different cations is extremely important here.
okay.
And that's why I think you have a much stronger driving force for salting out with sodium than with potassium, that is a larger cation and polarizable and cannot really form strong structures with water, not to the same extent.
Okay.
Right.
I didn't expand no, yes.
Yeah.
You're right completely.
Yeah. So the water, I was
Sure.
missing the water perspective.
Sure.
Okay. And yeah, you have actually two in this last chapter in two gels that you form at relatively low alkali concentration, below 0.25 molar. You don't really see this strong effect, right? Because those gels were not that strong. And that's probably because the gelation was not induced. And I mean, you couldn't induce gelation with this low base concentrations, right?
Yes. And for us, if I understand correctly, you mean what's happening after the drying and why it is like this, right? So the first part is to understand why the network is formed like this after coagulation, and this is the most important part. And for the drying, yes, because we have the difference in the pore size and the pore wall structure, where then we have difference in capillary stresses, and this is yes.
But it's probably because the driving forces for the initial gelation were different here.
Yes,
because
sure.
you didn't induce it by high alkali concentration.
Yes, it's very similar. That's why I showed here when we have acidic conditions. Yes.
Yeah, exactly.
So it must be very similar.
Yeah. Okay, so for my last questions, let's move away from this chapter and to the to your derivatization with amines. This completely impressive work that you have done, and there you were fighting a bit with the heterogeneous effect of your grafting, because you got a quite uneven distribution of the substitution throughout the gel. And you perform this in 2 steps, sometimes in 3. You have a first CDI activation, and then you have a reaction with amines. And you discuss about the diffusion of amines being one of the reasons why you get this heterogeneous distribution. But what about the first step? Can the very first activation with CDI also be the reason why you get this uneven derivatization?
We did not consider this.
Because
yes, you're right. It could be, for sure. It could be. We did not consider to check, because it's not easy to isolate the intermediate and study it. So we were always performing both reactions and studying the final material. And we did not test, try to isolate the intermediate and test different, different parts of the material. But we should, yes, we should consider this.
Maybe by performing very mild impregnation with the CDI first before heating, because once you start heating, then the reaction will start, and you will be consuming CDI at the same rate as, or simultaneously as it keeps diffusing into the gel. So I think, a mild impregnation at room temperature before you get the reaction started by heating.
I think it would be great if we had time to, if we were doing the reaction in low temperature, it's a very great alternative. I fully agree. And it was not too late, but we realized a bit late.
You have done impressive amount of work on that topic anyway, so this is just a detail.
Thank you very much.
Okay, I will stop here and congratulate you once again.
Thank you very much.
Thank you very much for those questions. So we turn towards Wim Malfait.
Thank you, and thank you for the great work, and also the readability of the thesis and the quantity and quality of the work you did, and also the presentation now.
Thank you.
And also the engagement with the questions. Some questions have been answered and discussed at great length. I want to quickly revisit the MTMS CVD, the chemical vapor deposition. You mentioned that you tried also grafting with the monofunctional silane hexamethyl disilazane. Is that correct?
Yes, correct.
Do you know the work of Satoru Takeshita on ketosane, where he did also a hydrophobization of ketosane, an amine-bearing polysaccharide with a monofunctional silane?
No.
Because there they saw that they could get the grafting, but when they did the supercritical drying after from methanol or ethanol, the acidic conditions in supercritical CO2 with ethanol basically led to the dissolution, like the bond was breaking, the silicon oxygen carbon bond. So they only could see it when they do the supercritical drying from another solvent like acetone, a non-protic solvent basically. So it could be the fact you don't see it in the end doesn't mean the grafting did not happen. It could be that the grafting had happened, but you've lost them during supercritical drying.
When we tried to modify with HTMS, we did not do supercritical drying in some cases, and we did not see any structural changes chemically from FTIR.
Okay, so that answers that concern.
So
basically.
we believe that it does not occur for pectine at least, or maybe we did not find good conditions.
But then what he also saw, and that's also why MTMS is probably the right strategy, is that this bond is then weak. You depend on one single silicon oxygen carbon bond, which hydrolyzes relatively easily. So long-term hydrophobization might not be that good. Then I have quite some questions on the polyurea pectine composites. You show in the reaction mechanism that you can have both urethane bonds and urea bonds. From the water, like the urea makes the amine from the isocyanate. What for me was a bit missing, how much water was in your sample?
We don't know exactly how much water we have. So we know that after solvent exchange, we have some water staying confined on the pores of pectine, but we have not identified the exact amount. It would be very low. Yeah. I don't know.
So that brings me then to the second question, because you always call them pectin polyurea composites. But
yes.
We don't know how much polyurea there is and how much is it a urethane coating on the pectin, which is a polyol basically, right? The pectin acts as a polyol. Is there any way you could answer this question?
Yes, we have seen that both we have the grafting and the polyurea structure. This we can see with NMR. We have done NMR, but we should do, what should we do? NMR would be nice to do, but not solid state NMR. And maybe because we could see with TGA potentially, but we don't see any difference.
I have no clear answer to
I
this
don't
question.
know, because in the TGA potentially we could see the different bond, the different groups, but we have just one step in for the synthetic polymer. So also IR cannot differentiate. them?
Then,
I don't know.
But let's assume they are both there. If you don't have a lot of water, it means you have a large excess of isocyanate, probably. Which normally in polyurethane foams, if you have excess isocyanate, you make this isocyanurate. Yes, the peer part. Of course, in your precursors, you already have the structure. So in the NMR, you see the isocyanurate structure, but that's also because your precursor, like they're shown here, they already have it. Do you know if you form extra isocyanurate structures, or have you not tried to see if this is possible to try and quantify?
I don't know. I don't know if we form more isocyanurate rings from our tricyanates. I don't know if it's stable. If we could form.
I also don't know, but I'm just, it's always called pectin polyuria, and for me, I'm not sure if it's pectin polyuria. That's sort of the question, because your loading of polyuria is not that high. It could also be a lot of
polyurethane.
But
urethane, yes. Yes, we should see exactly how it's connected, and if it's on the hydroxyl groups, the carboxylic acid groups, this we should check how it's bonded and where better.
Yeah. Then on the composites, I was a bit surprised that you compared, you discussed the U-shaped density dependence of thermal conductivity with the RF resins in the thesis, but now you showed also the graph of the pectin. It wouldn't make sense to compare to pectin or polyuria aerogels, not RF aerogels. I mean, I know this was the first paper that had this general discussion. This was like the groundbreaking work, but for your samples, the more relevant.
You said for which property? For the thermal conductivity?
The thermal conductivity, the density depends. You get this U-shape.
Yes.
And of course, here for pectin, there is this very nice paper, and also for polyuria, there is some information. So, but you showed it in the presentation, so that was clear to me. It also,
okay.
Then you did this compression tests, and you lower thermal conductivity upon compression. So for me, this tells me you're on the left side of the density of the minimum, which is also what you would expect because of the densities you had. Is there a reason why you can't go to higher pectin concentrations initially?
We saw that there was a study previously to correlate the properties with formulations, and we tried to select the best materials that had the lowest thermal conductivity. For higher concentration above 3%, thermal conductivity starts to increase, so it doesn't really go lower.
Okay. Because you get a lot of shrinkage. Yeah? You start with 2-3-8%, and then you end up with 0.09, not 0.03.
So we started with pectin that is in the minimum, and when we make the composite approach, because of lower shrinkage, then we are again at the left side of the curve.
Okay, so you started the minimum, but
yes. Okay, so we started to potentially be at the minimum, but at the end we were in lower density than when we would get the minimum.
Okay, yeah, understood. And then somewhere in that chapter about the compression, you question the very low thermal conductivity values at relatively high density. And that, I think you're right, this raises some concerns, and further investigation is needs to confirm this. I mean, with silica aerogels, we have seen the same, yeah? So, and then we hypothesized that this is due to the nature of the contact. These were hydrophobized silica aerogels, and then the new solid state contacts that occur on compression are not chemically grown, and maybe they're more like a point contact. Could something like that also happen? How would this be different in your materials, or would this also be like when you physically compress two nanofibrils fiber structures together? How is this different than a chemically made structure, let's say, during the coagulation and grafting?
So usually when we use more matter in our materials, we don't get reduced pore size after the end of the process. So we don't really get higher specific surface area. The matter does not contribute directly like this. And for sure, if we put more pectin or polyurea, we don't reach that low thermal conductivity. So in order to reach this low pore size, theoretically, we do it by compression. I'm thinking which parameter we cannot get the structure of that small pores just by changing the parameters of our pectin solution, for example. And we see that we don't lose porosity because the surface area stays nearly stable. So we have reduction, but we should not have closure of the pores.
I mean, my comment is more that if you do compression,
yes,
it's also maybe logical that you can go to higher density. With cellulose, is also strong alignment of the nanofibers in the cellulose upon compression, which is just a physical effect. Yeah, if you compress uniaxially, you will align the fibers. So it is a very attractive approach,
it is
but it's
to be
of course not very
tested.
practically feasible.
Good.
Then, if I have time, maybe one more question on the APD. So the last chapter of the thesis. They're really impressive properties. They're really nice SEM images, but the gels are of course coarser. Yeah, the pore sizes are larger.
Mm-hmm.
This is not a coincidence. Yeah, that the larger structures allow you APD. What are the main reasons you think? Like, what are the two effects that happen there? Like, why does a coarser structure allow ambient pressure drying?
Okay, so from the capillary pressure equation for the Young-Laplace equation, we know that the capillary pressure is directly connected with the pore size. So the bigger the pore diameter. So the bigger are the pores, the lower are the capillary pressures. So in that case, we have bigger pores, so we should have lower capillary pressure compared to few nanometers, like 15 nanometers. And the next parameter that we consider that is very important is that we have much thicker fibrils of pectin, and these have much better mechanical strength than the fibrils that may be 1/10 of the width. So a combination of lower capillary pressure and better mechanical properties of the network, we think that together they allow us to have open structure during evaporation.
So this is, of course, it works, but it means you have to compromise the performance to get the APD. Do you have any ideas how one would try to push this to have less of this compromise?
Yes, I mean, we need to test the limit of this balance, let's say, and this our thinking is that we need to try different. I mean, first of all, we need to understand the exact mechanism of network formation that we've been discussing all this time, because it's not clear why we have this specific formation. And by understanding this and changing maybe the base, or if we can put other molecules, maybe cross-link the network to reinforce it better, then we could see if it could reach super-insulating properties. Maybe not 15 milliwatt per meter Kelvin, but why not? I mean,
I would also certainly suggest, I mean, probably not you, but to try the drying conditions themselves, because for silica, it's very sensitive to like gas pressure, temperatures, solvent composition, like so there's a lot of room also with a given structure, just by changing the drying conditions, that there might be room to optimize to try and push that boundary.
If I may comment on this, because we see this structure for aerogels as well. that they are supposed to preserve the structure, that they still have shrinkage and they don't really preserve. So already before drying, the structure is not ideal probably for super insulating properties. So of course, the drying process needs to be studied, but I think it's to reach better insulating properties, it would be more, I mean, not worth it, but for me, the focus should be more.
You shouldn't try it on the pH 13 sample. Yeah, you should try it on the pH 7 sample or,
Yes.
or something in that range.
Yes, yes.
Yeah, thank you.
Thank you very much.
Nice to meet. Thank you for that. Nice to meet you. Yes, but already meet you. So thank you for this. I would like to thank Tatiana and Arno for and Julien for being invited. I will not be the one who will be the exception to congratulate you.
Thank you very much
for this job. So the manuscript, the presentation also, which is very clear. It's always good for us who produce pectin for food to see that we can also use pectin for something else than food. Which bring also some question, of course. I would like maybe first to bring some comment on some question who arise and to support you on some answer also. Because yes, so you didn't work on product which do not exist on the market. This is really product which are commercially available. So if tomorrow we would like to do that, we are able to provide the pectin for that. So this is first comment. So next, the question of how it is realistic. So this is something else, because of course, in terms of costs, even if pectin is a well-known polysaccharide, which can appear as low costs, just it's 10 to 20 times the price of cellulose derivatives. It's 50 times the price of starch.
Okay.
So just to give you an idea. And of course, then there is a question of volumes, because today the pectin market is designed mainly for food. And if tomorrow you come with another application, we consume, I don't know, plus 50% of the volumes, worldwide volume, so it will be an issue. But we are not at that stage. But for sure, I really appreciated that in your conclusion of your manuscript, you mentioned, and in the answer also, that maybe the future will be also to work with a less refined, less refined pectin, even if it will bring for sure other difficulties, because less refined mean closer to the citrus pills, for instance, so meaning that you will need to deal with cellulose, hemicellulose on top of pectin. So not so easy. I would like also to come back to the molar mass of the pectin. So as you said, today in food, so it's quite old market, I will say. And basically we have two types of pectin. So the high methoxypectin, so HMP, and low methoxypectin. And usually people are using this pectin according to the application and based on the DE. So then you have, of course, the effect of the molar mass. So we can provide different molar mass, but this is not the main driver for using pectin. And pectin is not a good viscosifier. So the molar mass that you presented somewhere,
yes.
there are, I'm talking about the zero concentration of bases, is more or less, it's quite common. It's not so huge, but this is, we cannot do much more, I will say. So, and this is quite low versus other polysaccharides that you can find. So the positive point is that finally one of the good products that you succeeded to obtain is using quite low molar mass pectin, so which demonstrates that finally we don't need to have the bigger polymer to obtain the a good structure. So this is for me a very interesting point. So I still have some question. I will maybe do a shortcut, which are maybe not scientifically right, but I have the feeling that in order to avoid collapsing, so it's mainly on the last chapter, chapter 6. In order to do not have collapsing of the network during the any drying, so you need to have a network which is quite strong in order to resist to some capillary pressure, especially when it's not supercritical dry. So it brings me to the question that, okay, so this network, how you create it and how do you control the structure of this network? When you talk about organogel, as you said, this is kind of it. This is precipitation. So for me, this is not a well controlled network. Especially, I have even some question if you can come to a picture when you show the gel. So on the slide 25. So here the non-solvent are on the top, and so that means that at some point you need to add alcohol, for instance, on the top of a solution, because it's not a gel, a solution, and so then you start to have a precipitation probably at the interface, and then you have progressive exchange of solvent, and for sure the network is maybe not so well controlled. On the other hand, when you treat with sodium hydroxide, you also demonstrated that when you don't use a lot of sodium hydroxide, the network is not so strong to resist to a regular drying. So it brings, again, the fact that potentially it could be great to have really an hydrogel. So meaning a 3D structure before the exchange of the solvent, and to design an hydrogel which is strong and we can resist to the solvent exchange and then to the drying, and ideally to evaporative drying. So finally, my question, sorry, I was quite long, but low methoxypectin is well known to gel, to do hydrogel with calcium. I know that it was done in a previous work, but I do not know if why it was not investigated in your thesis. And the second question is that, do you think that it could be worth to potentially spend more time to characterize the hydrogel, so before the organogel, before the solvent exchange, to really determine what would be the more suitable?
Yes, thank you very much. So starting from the beginning, for the calcium and the gel structure, always when we have cross-linking and gel formation before drying and not just by coagulation, we have a more sturdy structure. So we know that for the same exact formulation of concentration, pH and non-solvent, when we have calcium cross-linking, we have less shrinkage during supercritical drying. However, this is not enough to avoid avoid it, supercritical drying. So there have been tests like in previous studies, and by evaporation, at least in vacuum, they were not successful, even if they were calcium cross-linked. Why we don't use it is that in some cases we want the carboxylic acid groups to be accessible for modification. And the second thing is that it's a bit tricky sometimes to do the cross-linking with calcium, because by the time calcium is touching pectin, it's gelling directly. And the way to diffuse calcium homogeneously in the structure is not evident. We can do it by adding extra molecules to slow down the gelation and be homogeneous. People usually do it by diffusion, either in bath, either in membranes or filters, and this is not homogeneous at all. I don't know if it's more homogeneous what we do, but at least in chemistry point of view, we're homogeneous. So it was tricky. The first part is for the accessibility of the functional group, and the second part is for the feasibility, let's say, of the cross-linking. However, it would be very interesting to do, but we need to do something to go with, to be honest. Then for the structure of the gel, I wish that we could have the opportunity to characterize our gel every time, but unfortunately the methods are very specific and very expensive, to my knowledge. Usually you need very special equipment, like for environmental SEM, it would be great to see the structure. The porosity, I think I'm not sure if you can see the porosity in the gel, like in some beam lines with some techniques. So to my knowledge, it's very tricky to characterize the gel, the structure of the gel, the pores. But for sure, like the gel is the most important part if we can control the gel. And for the structure of the network, we could potentially make the same structure, not by, if we confirm that the combination of lower capillary pressure and higher mechanical strength of the structure is what let us perform evaporative drying, then we could potentially find cross-linking methods that we can have the exact same structure, avoiding deesterification, depolymerization, of course. So yes, gel is very important, I agree. And we see it always through the aerogel. That is not, we consider it as the most representative structure, but it's not the real structure. So yes, for sure, there are so many things to do.
So, on the first point regarding the use of calcium and low methoxy pectin, because it's not working with high methoxy pectin, the gelations and cross-linking with calcium. So I'm pretty sure that we can discuss on this point, because we succeed to do low sugar jam with such kind of pectin and using calcium. So I'm pretty sure that if you succeed to do jam, we can do some network. Especially, in fact, there is a trick for progressive calcium release into the medium, in order to, you're right on the fact that it's very fast. The gelling is very fast, so it can bring some difficulties of homogeneity when you want to have a bulk, gel. But if we can work. There is some astuce.
We just, we try to avoid adding more parameters in the system, because already non-solvent concentration, pH were parameters. We try to avoid having in addition the calcium content, because our main goal was to modify, to prevent aging. So when you find the suitable modification, then you can adopt like the way to make the pectin gel. Now for the evaporative drying with the base, this is another story that it was surprising working well. So yes, we consider it a lot, but it was, I would say, a hard decision that needed to be made at the very beginning.
And for the characterization of the hydrogel, I was more thinking about kind of rheology, you know, evaluate the G prime, G double prime, and maybe it's stupid, but maybe it can be a way to predict how the shrinkage will you know, occur during the solvent exchange, but it's maybe something which is already known. I don't know.
Yes. For pectin gels, they don't. Cellulose. We haven't characterized the G prime, G double prime of our gels. None of them. We could, yes, sure. I didn't think about it when you asked. Yes, sure. A correlation would be, yes, it would be very nice to know in advance.
So thank you. thank you very much.
Thank you very much.
We are mostly done with questions, but probably your supervisor still have a few words to say. So we will start with Julien Jaxel.
So first, I will not be the last person, but not the first person to congratulate you for this nice presentation. And well, you were quite impressive in terms of efficiency in the experiment and willingness to learn all the techniques. So what maybe the external members of the jury don't know is that Eleni always asked to do the entire processes, like CO2 drying herself, BUT was done herself, and also SEM, which is quite rare in our labs. And that shows a deep scientific analysis of the result and a deep curiosity about the techniques, and always trying to ask me a lot of questions about the techniques, which in many cases I didn't know the answers. So that was good also for me. Then Eleni went to a lot of conferences and scientific exchange, and I would like to thank her also for always bringing back chocolate and small gifts. So bad that our students are not there. And yes, it was, I mean, perfectly clean in the labs, which is, well, I have to tackle these problems too. But Eleni was, well, really asking a lot for cleanliness in the lab, which was really good, and things that the jury might not see, but is really nice. Well, I will stop there, not ask questions, because you were already grilled with a lot of questions, so I will stop and just send the mic to Arnaud, maybe. Congratulations again.
Thank you.
So Eleni, to be exotic, congrats. Congrats and congrats.
Thank you.
Before coming back to you, thank you very much for the members of the jury. It was really a pleasure to have you with us today, and many excellent discussion and points like, okay, BGH applied to such material, okay, very strange, compression of material, and even low thermal conductivity. So it was really interesting to have this discussion today with expert Eleni, and you answered very well. So you make, as it was already said, impressive and great work. And I must also add that it was really a pleasure to work with you and the team, Tanya and Julien, for these 3 years. And I underline and I set off really, really strongly 3 years, because in my mind, it is rather a kind of challenge and a big success to do this, all this in 36 months. This is not the rule. This is not the average. You really want to, and you achieve in doing this. So congrats again for this.
Thanks.
And before I'm going to be to stop, but I do hope that someday maybe we can meet again. This is my first hope. I know you have changed your mind regarding the beginning of the story 3 years ago. Okay, going on in the academic research field was not the priority, and you changed your mind, and I'm really happy also for this. It seems that you liked working on this topic in the laboratories and in the public research. It is a very good point too.
Nice.
So thank you very much, and I'm sure that you are going to have a big career.
I will be coming back bringing chocolates. Thank you very much.
The last not least, so thank you again, the committee members. What I said this morning, I know that that's a job, that's time and efforts to read the thesis, for the rapporteur and for the reviewers to write the report. I really appreciated your reports, because they show that you read the thesis. It was not the artificial intelligence that who wrote the report, and you thought about the results. You made very interesting, valuable comments. So really, thank you very much. And thank you all committee members, because coming, you are not in your labs, you are not writing projects at this moment. So that's very appreciated. Thank you. Thank you, Sylvie, also to take time for following and not switching off the screen, which is also very appreciated. You are with us. Okay, sorry, you will not join lunch. So a few words about the work and about Eleni. So when we were discussing with Arnaud building this project, we put extremely high challenging objectives, which we knew, we were saying between us, that it will not be possible to reach. Okay, something will be done, but practically impossible. Then Eleni came. Eleni is she's an excellent scientist. First, she is a very great team member. She is soft, but she is hard also. So she knew what to do. We discussed a lot, but she was going to the topic, to the goal, and she had objectives, and I think this is very important in life, to be a bit strong, and not listening to supervisors, but also very softly, but pushing a little bit, very softly, but advancing, and you did extremely well. As everybody said, you did a great job. I was at the beginning, I was not at all expecting these type of results, that this could be managed. With your last slide, with the different conclusions and prospects, you really opened a lot of interesting directions, because for those who are not very much in bioaerogels area, there are still young materials. There is a lot of literature with confusing results, problems with characterization, not understanding many things. There are much more things that are not understood than what is understood. And Eleni brought in each part a big stone, to understand, to move forward. And this is what was shown by the questions and by the answers. All results are very interesting, and there are a lot of prospects. So I'm regretting that you finished your PhD. In fact, we could have continued working for many years. That's because there are still many things, and it was really a pleasure to work with you. So thank you very much.
Thank you very much. I would like to make a comment myself, if I may, and express that this is not my work, it's a collaboration. As Tanya said, I'm a good team member, but I also have a great team. So this is our team I mean, I was in the lab, but of course, it's very important. So that's this.
Okay, thank you. So we'll close the session now. So the jury will go for deliberation, and then we'll be back in a very long time, I think.